Today we'll be reprogramming one of the most essential STL containers there is in C++, that being the std_vector class. So let's first talk about what makes the std_vector class so special. It is the fact that it's regrowable throughout the runtime of a program. So if we have some kind of array right here, we have to specify its size at compile time. So here we say that it contains 3 elements. And if we would want to access a 4th element at the 3rd index, you can see right here that that doesn't work. Since it isn't regrowable, it won't adjust to your needs. If you say it's 5 elements, it will remain 5 elements and it won't change. It won't grow, it won't shrink, it will always stay the same, it's static. Now with std_vector, that isn't the case. You don't have to specify how many elements you need at construction. It will just adjust based on how many elements you put in. So it might allocate room for 10 elements, and as soon as you exceed that, it will allocate room for 20 elements. Then if you exceed that, it might allocate room for 40 elements. So it always adjusts to your needs without you having to deal with that. So let's create the header file for this class and also declare it. Since this is part of the STL, it's a templated type. And let's now declare this class vector. And now let's talk about what such a class might need in terms of its fields. So the vector class is something we call a sequential container. A sequential container stores all of its elements in memory next to each other. So it wouldn't put, if you have 2 elements, it wouldn't put one element at location 100 and the other at location 20. It will store them next to each other. So if you have 2 ints, the container might store the first one at location 4 and the second one at location 8, since each int is 4 bytes on a 64-bit architecture, usually. So yeah, let's first create a pointer to the first element and let's call that the data. So this pointer will point to the first element, and now we'll also need some kind of size indicating how many elements there are in the vector. So if you have 2 elements, there will be 2 for the m size. Now size is initially 0 and m data is initially a null pointer. Doing this also works, but I like to be a bit more explicit. Now, you might already think that those 2 are enough, but let's think this through. What will happen if we try to add an element? So say it's at the beginning it's 0. Then you'll probably add an element like, I don't know, 1. And then m size will increment and the m data will also allocate new memory on the heap for one element of type t. Now say you add another element, then m size will be 2, and now it will have to reallocate room for that. Now say you add another one, then it will be 3, and now it has to reallocate room for 12 bytes of memory, and we'll always have to reallocate that memory each time you add an element, and we'll always have to like make that request, okay, give me 12 bytes, give me 16 bytes, give me 20 bytes in the heap. Now you can see how this can become very inefficient if you have 100 elements, since each time you would add one, you'd have to reallocate room, move all of the data from the old place to the new place, adjust all of that, and this operation of reallocation, it's very expensive. It shouldn't be done each time you add an element. So what we could do is we could say, okay, we have another field called the capacity, and this capacity is like telling us how much room we've pre-allocated. So say we add an element and the size grows from 1 to 2, and we know that, I don't know, the user will probably add more elements. Let's already allocate room for 10 elements in the heap, so we won't have to do that reallocation for another 8 elements. So yeah, let's start implementing this pushback method, which will take a value of type t called element, and the insertion of this element will be pretty simple. We'll just go to the mdata, and well, if we have 0 elements, the new element will be at location 0. If we have 1 element, the new element will be at location 1 or at index 1. So the new index will always be the size, and after adding it, we'll increment the size. Now, if we were to run this as of right now, you'd already assume that we'd get a segmentation fault, right? Since we're accessing memory on a null pointer. So what we have to do is we have to check, okay, is a resize necessary? And a resize is necessary if the amount of pre-allocated elements exceeds or is less than the size. So if the size exceeds this capacity. So if the M size is bigger or equal to the capacity, then we need to do this reallocation. So let's call a method called realloc. And this realloc method we'll define right now. All realloc does is it allocates room for how many M capacity we have. So say we have 10 M capacity, then it will allocate room for 10 elements of type T. And it will move all of the old data over to the new data and reset it. So set that M data to the new location in heap. So let's first create this new elements by calling new T and putting in the capacity. And the M data is now equal to this new value. Now you can probably already see that this on its own isn't enough, since all of the old data would be lost. So let's keep a reference to the old data. And now we have to move or copy all of that data over to the new location, which is living in M data, or which sits in M data. So we'll have to do that for M size amount of elements. And what we'll do is we'll say, okay, M data at the index of I is equal to the sit move data of the old data at the index of I. Why do we move it? Well, we'll be deleting it here anyways, so there's no need to copy it and preserving its internals, since we're deleting it here anyways. Now, you might already think, okay, that's enough, but it isn't, since we still have to reset the capacity. So if we don't set the capacity equal to some other value that is larger, then it will always remain at 0, and that doesn't work. So let's first check if capacity is 0. If it is, then we want an initial size to have of 2. So let's create a constant for that called initial capacity, and let's say that's 2. So we want to avoid magic numbers, and let's also spell initial right. Initial, okay, and otherwise we want to grow it by some kind of factor. So if we have 2 elements, we want to grow it by 2 or double it, so it's 4, then 8, then 16, then 32, and so on. So the factor is, for example, 2, and then we say M capacity times the factor will be the new capacity. And now we'll reallocate, and that should already be it. It still isn't, it still creates memory leaks. We'll fix that in a second, but let's first see if this works. So create an instance of the vector class, and we need to specify the type, the template type. So it's of type int. So we'll push back 1, and then we'll push back 2 and 3 and 4. And let's now add a method that are some kind of way to access elements, and we can do that by saying, okay, we'll create an operator overload for the brackets, and it takes an size t in there, and then we'll return M data at the index of I, we won't do any bounds checking since that should just be a segmentation fault for the user, or undefined behavior for the user. And if we were to print out the element at index 2, then we'd expect 3 as an output. So let's see if that already works, and it seems to be working, which is nice. Yeah, now the standard also offers a lot of other methods, like, I don't know, size, where we return the size, or something like shrink to fit, where we set the size or the capacity to be the size, and then reallocate to not use more memory than necessary in the heap. But you can take a look at all of these kind of methods and try to recreate them yourself. The only thing I want to do now for this video is to to make this memory safe and copyable properly. So since we manage our own memory with this mdata, we'll have to create our deconstructor where we delete it. And if you know the rules of 5, you can already tell, okay, if we declare a deconstructor, we should already be thinking of declaring a copy constructor, a copy assignment operator, a move constructor, and a move assignment operator. So let's do that. So let's first declare the copy constructor. This will take an element of another vector, so another vector that also stores elements of type name t. And what we'll do in here is pretty simple. First what we'll do is we'll set the capacity, our capacity, to the capacity of the other vector, and we'll do the same for the size. Now the data we can't set, so we can't just say mdata equals other.mdata, because then they're pointing to the same location in memory, but we don't want that. We want a deep copy. We want to have an exact replica of that. We don't want to have the exact same thing, right? So what we'll do is we call realloc to have m capacity amount of elements ready in mdata, and now we'll just iterate for m size amount of times. And what we'll do is we'll say that mdata at the index of I is equal to other.mdata at the index of I. And with that, we've successfully copied it. And now let's also define the move constructor. And what this one does is a bit more simple. So similar to this, we'll also set that. So we'll do that first. But instead of like actually copying it over and preserving the state inside of other, we'll just say that mdata equals other.mdata, and now we'll also hollow the other object out. So we set other.mdata to a null pointer, and that is the only important thing to do, since when the deconstructor of other is called, this mdata will still preserve. So we definitely have to do that. Now optionally, you can also set m size and m capacity to 0, since semantically that is what a hollow object is, an object of 0 bits, so like cleared out. But yeah, that's kind of optional. Now after defining the move and copy constructor, let's do the same for the copy assignment operator and the move assignment operator. So if other equals this, then we just return, since otherwise, like you'll see here, we'll immediately delete mdata, since we will be resetting it here anyways. So if we were to set it to the same thing, that would be it wouldn't like work, right? Because we delete it and then also set it, so that would be very weird. So we'll just still be deleting it here. And let's also return this so that we can do stuff like a equals b equals c. So that's why I set that to be the return type. And now let's also define the copy assignment operator. And let's do that in here. Now we won't do this, we'll just do basically this, and return this pointer. And yeah, that seems to be working. So let's try it out. Let's create another numbers2. And yeah, since we defined all these constructors, we have to manually specify the default constructor. Yeah, so let's set or initialize numbers2 with numbers. And now let's call numbers.pushback3, and let's get numbers2.size. Oh no, let's just print numbers2 at the index of 3, and that should be 4 if everything ran right. Oh, segmentation fault, damn. Why is that? Yeah, well, I'm kind of stupid. You have to do it like this, right? Because otherwise it would think that m size is still the new size, but it's the old one. So yeah, we have to do that. Yeah, and you can set m size to 0 in here. That's also valid, so that we don't move any data, since it is 0 at the beginning. So yeah, just do that. That works, right? And let's do the same for the copy assignment, like that. Now, if I try to build this again and run it, yeah, it works fine, as you can see here. And doing that will give undefined behavior. Oh, it's 0, which is nice, but that isn't insured, right? Like it's completely, that could be anything in here. So yeah, well, that's pretty much it for the vector class. You can add all of the other elements that there are inside of this class, like just take a look at CPP reference. But yeah, we've properly implemented this vector class.